These are the solutions to the Chapter 11 quiz. This first question just teases out the difference between the population of all households and the sample that was actually surveyed. So each one, the population and the sample, is going to have its own mean, its own standard deviation, and its own size. In the second one here, we have an original distribution that's certainly not normal. It's got a very heavy right skew, but we continually take these random samples of 25 households and then get the mean, and then another random sample, get the mean. So we're looking here at the distribution of sample means is what we're asking about. This is the original distribution. We're looking about the distribution of sample means. Like we talked about in class with the movie time lengths or the card values. So what would be true about the distribution of sample means? Remember, it doesn't matter what the shape of this original population is. The shape of the distribution of sample means will be roughly normal. We also know that the mean of that distribution of sample means is going to be the same as the mean of this one, which was not given, but we know that it's the same one. The standard deviation does have a correction factor. Remember that you have to divide by the square root of n, the square root of the sample size. Here we're doing samples of size 25. Square root of 25 is 5. So the standard deviation of that distribution of sample means that new distribution we create will be much smaller. In fact, it'll be 1/5, 1 over the square root of 25. Okay, here we have an SAT that's scores are normally distributed. We have the population mean and the population standard deviation. We take a random sample of 100 students, and then we take another random sample of 100 students, get the average score, and so on. What's the average of all of these averages? Well, central limit theorem tells us that's just the population mean. The mean of the distribution of sample means is just the original mean. Here we do a similar thing, so SAT, exam scores, and we do take a random sample that has a sample standard deviation. What's the best estimate for? Notice what we're looking for here. We're looking for the standard deviation of all the students. In other words, the standard deviation of the original population. We're not looking for the standard deviation of that distribution on the right side, the distribution of sample means. That's not what we're doing, at least not in this question. We're trying to estimate the standard deviation in the original population. And remember, our sample is kind of a miniature version of the population. So that 90 is really going to be our best estimate at the population standard deviation. Now, what you may have been thinking about on that previous question is what's the standard deviation of the sample means. So now we're talking about the distribution on the right. Now we're talking about taking 100 students, getting the mean, taking another 100 students, getting the mean, and then looking at how the shape of all these means plays out. In that case, we have to take the original standard deviation of 115 and divide that by the square root of n. Divide that by the square root of 100. Square root of 100 is 10. So we divide 115 by 10 to get 11.5. Notice that that's much less than the original standard deviation. That distribution of sample means is much more squished together. It has much smaller variance than the original population. Okay, here's a little more intense computation. Key part here is we have a normal distribution and we have a single student that we're concerned about. We're not taking an entire sample of students here. We're just looking at a single student, and we want to know what's the chance that their score would be above 35. Well, what we would use is the z-score z-score formula that is what we learned back in Chapter 3, because we just have a normal distribution, a population that's normally distributed, and we're comparing an individual to the rest of the population. So we're taking that individual score, 35 in this case, minus the population mean, 25 in this case, divided by the standard deviation. That'll give a z-score, which we then look up in Table A. Okay, we had a z-score of 1.54. So remember, the z-scores are on the margins here. Inside is the portion of the normal distribution that's to the left that's less than that given z-score. So 1.54 would put us right here, 0.9382, which tells us 93.82% of the normal distribution is below a z-score of 1.54. However, because we want the percentage of scores that are greater than the cutoff, we need to subtract that number from 1 to get 0.062. So 6.2% of the scores would be higher than this student. That's for an individual student. What question 7 does then is takes a look at what if you take 100 students. We still have the same mean and standard deviation there of the original distribution, but now we're looking not at an individual student, we're looking at a sample of 100 students. And we want to know what's the chance that when we take the mean of our sample, it would be above 27.0. So we need to use a similar formula. Notice that we're still using the same relationship here that we had original z-score formula. We have something minus the mean of all those somethings divided by the standard deviation of all those somethings. And we can rewrite this to simplify a little bit, because we know that the mean of the distribution of sample means is just the original population mean. And we know the standard deviation of the distribution of sample means is the original standard deviation, the standard deviation of the original population, divided by the square root of the sample size. So this is the z-score formula we need to use for this problem. Okay, when you plug those numbers in, keeping in mind that 27 would be your value for the x bar in that formula. When you plug all those in, you should get a z-score of 3.08. I'm going to look at the 0.08 column there, go down to 3.0, so right here, 0.9990. In other words, 99.9% of the sample means on this distribution will be less than that average score of 27. Of course, again, we don't want less than, we want greater than, we want above. If this had said less than, we would have left that 0.9990. Table A always gives us the area to the left of a given z-score, or less than. Since we want above, we'll subtract that from 1. 1 minus 0.999 gives us 0.001. The final question here is going to move us a little bit into the next section, but you have a dice that you're rolling over and over again. Feel free to just set up a spreadsheet, do a lot of equals ran between 1, 6, and then take the average all of them. It should give you something pretty close to 3.5. You can also do this mathematically. Essentially, you're taking the average of all the possibilities, since they're all equally likely. So if you add up 1 through 6 and divide by 6, that'll give you 3.5. But don't be too concerned about that last mathematical method. More importantly, that you do know how to simulate questions so that you can get a good estimate to the answer.